Section 9.4, the temperature composition diagram and fractional distillation. So we'll look at this temperature composition. This is Z-benzene. So this is the overall mole fraction of benzene in both liquid and gas phases. And it's mixed with toluene. So over here you have 0% benzene. That means 100% toluene. And over here you have 100% benzene and no toluene. So by looking at this phase diagram, we can actually get the boiling point of pure benzene, which is over here. It's roughly 353 Kelvin. That's 80 degrees Celsius. What about toluene? Toluene has a much higher boiling point over here. It's 385. So that's 112 degrees Celsius. Now let's look at this TZ diagram. Assume this is a nearly ideal solution because benzene and toluene have very similar molecular structure. Let's start with this point A here. At point A, it's 100% liquid phase, and let's look at the percentage of benzene. It's roughly 11% of benzene and 89% of toluene. So it's mostly toluene, just a little bit benzene. And somehow we can purify this solution and not to get pure toluene. We're going to get pure benzene. So it's only 11% of benzene, and yet our goal is to get high purity benzene. Okay, high purity benzene. Alright, how do we do this? It's very simple. So at this data point, you can see this is a horizontal line. So we're going to do this liquid to vapor phase transition at this temperature. So basically you just want to make sure the temperature is roughly constant, yet you keep adding heat to this liquid. So you can gradually convert this A to point B. Alright, from point A to point B. Not 100%, okay, not 100%. So really, I want to make it more clear. You have to kind of start with a mole fraction a bit higher than B, so somewhere here, okay, somewhere here. It's going to be between A and B, all right? And then allow this system to reach equilibrium. And this segment will be the number of liquid, the number of moles of liquid. The small segment will be the number of moles of the gas. But look, in the gas phase, the mole fraction of benzene is B. That's 25%. In the liquid phase, the mole fraction of benzene is A. That's 11%. We talked about it. So really, you need a mole fraction actually higher than 11%. So somewhere here. Just a little bit higher than 11%, and then you allow this system to reach equilibrium at this temperature, and then you have the liquid phase. How much? This much. And then you have the gas phase, only a little bit. But in this a little bit gas phase, you have a much higher mole fraction of benzene, now 25%. You collect the gas phase only. I know you're going to waste a lot of chemicals, but you just collect that a little bit. Again, this is just a little bit gas phase. If the data point is here, you just collect a little bit gas phase. Don't worry about the liquid phase. Just collect the gas phase and cool it down. Cool it down to C. Okay, cool it down to C. Actually, it has to be kind of either this data point, if possible. If not possible, a bit higher than there, so that you can have two segments. This segment is going to be the liquid phase. This segment is going to be, this segment is going to be liquid phase. This segment is going to be gas phase at this point. So it's not really exactly here. This phase diagram is a little misleading. You cool it down to a temperature a little bit higher than C, so that you still have two phases. You have the gas phase a little bit and liquid phase a lot. So now if you look at the gas phase, well, the gas phase has a higher mole fraction of B, benzene. It's now 40%. and then cool it down to a data point slightly above E. Again, this is just to ensure you have two segments, a really large segment for liquid phase, very small segment for the gas phase. Collect the gas phase, because in the gas phase you have a higher mole fraction of benzene, which is more than 60%. Cool it down and keep doing this, cool it down, keep doing this, cool it down, keep doing this is 95%, 90%, 95%. So in the end, you get 97% of benzene. All right? But I have to tell you this. If you start from 1 million moles of the mixture, in the end, you probably get just maybe 0.1 mole of 97% benzene. Okay? You start from 1 million moles of the mixture, and then you end up with only like 0.1 mole of very pure benzene. Of course, don't throw away all those liquid phases. They can be used to make pure toluene. They can be used to make pure toluene. All right. So, but of course, you just somehow you have to kind of go up. You have to go up to get pure toluene. We talked about benzene and toluene. When you mix benzene and toluene, it's a nearly ideal solution because these two have very similar molecular structure. The interaction between benzene and toluene is very close to the interaction between benzene and benzene, or between toluene and toluene. What if you have non-ideal solutions? You pick two molecules, they have different structures. The interaction between A and B is quite different between A and A or B and B, and then you observe some abnormal behavior. All right, so again, we're looking at this, the temperature versus composition, but this composition is X, we're just talking about the liquid. In this case, A and B attract each other more than A attracts A or B attracts B. So if A and B attract each other, well, in the liquid phase, they are close to each other, they attract each other more than AA and BB, then you can imagine that attraction stabilizes the liquid phase of the mixture. It stabilizes the liquid phase, and that makes the boiling point higher. So this is the boiling point. This is the boiling point of the mixture, higher than the boiling point of B, higher than the boiling point of A. All right, higher boiling point because the liquid phase is stabilized. Well, somehow A and B can also repel each other. I put this repel in double quote because it's not really a repulsion. It's just the AB attraction is smaller than the AA attraction and AB attraction. So it kind of feels like A and B repel each other. It's just they don't like each other that much. And then that will destabilize the mixture compared to pure A and pure B. So over here you have pure B. This is the boiling point of pure B. This is boiling point of pure A. But when you mix A and B, because they don't like each other, they prefer to escape from each other. That makes the boiling of the mixture a lot easier. That means the lower boiling point over here. There are technical terms. We call them maximum boiling azeotrope. When the two chemicals attract each other, you have a higher boiling point for the mixture. One example is acetone and chloroform. Acetone has this boiling point 57, chloroform's boiling point 61. But if you mix chloroform and acetone, the boiling point is higher than this one and this one. It's 65 degrees Celsius. Again, this is because acetone and chloroform attract each other. Well, why? Because in acetone, you have a carbon and an oxygen both partially charged. Carbon is positively charged. Oxygen is negatively charged. In chloroform, you also have a carbon and chlorine both partially charged. And in this case, it just happens that in chloroform, this carbon is attracted to the oxygen in acetone. And the chlorine end is closer to the carbon in acetone. So there's strong electrostatic attraction between chloroform and acetone. Let's see. If we look at this minimum boiling azeotrope, this is when two chemicals repel each other. For example, toluene and acetic acid. Toluene is just the benzene with one methyl group. So the boiling point of toluene is 111 degrees Celsius. That of acetic acid is 118 degrees Celsius. But when you mix them, the boiling point is lower, much lower. It's only 100 degrees Celsius. All right. So at least 10 degrees Celsius lower when you mix toluene and acetic acid. That's just because they don't really like each other, or I want to say they like each other just a little bit. The attraction between toluene and acetic acid is much smaller than the attraction between two toluene. It's also much smaller than the attraction between two acetic acid. That's why the liquid phase of the mixture is destabilized. It's a lot easier to boil the liquid phase.